Hello, my name is David.
My name is Yuxuan.
And I'm James.
We are all from Modeling College.
And this is our gravity-based pendulum clock.
I'm James and I was responsible for designing and building the pendulum and escapement mechanism. For the pendulum, I approximated the length using t equals 2 pi square root L over g. Obviously this was an incredibly rough estimate, as not only is there friction involved between all the joints, but the pendulum is swinging with a large amplitude and it's being driven. So the equation isn't really applicable, but it did give me a good estimate. The escapement was the next thing I built, which is this anchor and the escapement wheel here. And this controls the descent of the weight, allowing us to have a consistent rotation of the axle, which corresponds to consistent ticking of the clock. The escapement is also responsible for the very attractive ticking sound which the clock produces. As the pendulum oscillates, it is driven by the force of the weight falling and rotating the escapement wheel, which in turn drives the pendulum at a constant period. We also ensured this was a consistent period over a large amount of time by using this light sensor, which recorded the light intensity over time and gave us a very nice sine wave of the pendulum going closer and further away, which allowed us to accurately estimate the time period, where we got 1 second for 3 significant figures.
My name is Yuxuan and I was in charge of the construction of the winding system. In order to maintain the motion of the pendulum during rewinding, we designed a differential system here to separate the torque transmissions for the winding process and the movement of the clock. The ratchet here, next to the motor, permits the axle to move in only one direction. Basically, the differential system ensures continuous operation of the clock. After that, we also designed an automatic rewinding system to avoid manual intervention. The system detects the movement of the driving weight through a touch sensor here. Every time the driving weight moves for approximately 90 seconds, the little rod here will touch the sensor, triggering the motor to rewind the weight for several seconds. After which, the rod will go back to its original position. Therefore, the rewinding process is periodic, avoiding manual operation. The real challenges here are how to find the most suitable triggering method and how long the motor should run to rewind the load without touching the sensor again. The solution to those issues is basically trial and error, and we think we'll tackle it in a reasonable method, the reliability of which will be proved in a time-lapse video for the continuous 1-hour operation of the clock later on.
Finally, the clock face, which was arguably the simplest section of the clock to build, considering that it is fundamentally just a gearbox and I was able to work on it independently of the rest of the clock. As you can see, there are 3 hands, seconds, minutes and hours, therefore requiring a gear ratio of 1 to 62 3600. To achieve these rotation speed factors of 60 between the hands, I had to put together the appropriate pairs of gears, using the ones available to us, ranging from 8 to 40 teeth. A realization I made during the process was that the torque generated by the main mechanism would have to be provided to the second hand initially, and not, for example, the minute or hour hand. The reason for this is that starting with such a high gear reduction leads to a significant increase in torque demand, which would create resistance, subsequently causing the gears to slip, which I experienced firsthand. A persisting issue as well was ensuring the structural rigidity of the gearbox, hence why it looks as ugly as it does, but to be honest, I don't really care because it works and it gets the job done. Our team had a slight crisis once it came to connecting the gearbox with the main clock mechanism. For some reason, we tried to increase the rotation speed leading up to the second hand, which would have essentially created a 1/60th of a second hand. This instance of storm damage caused gears to slip, and eventually, upon receiving flashbacks to year 3 maths, we noticed this and instead slowed down the rotation speed accordingly, leading to a second hand which revolved once every 60 seconds as required.
Thank you for watching.